Okay. Now, as we have fit linear, the form of a linear function to data, or fit 3 points on a graph to a quadratic function. Okay. We can fit any 2 points on the, well, in the first quadrant at least, and more generally, as long as they're on the same. Well, okay. We'll just stick to the first quadrant. Sometimes that makes a difference, sometimes it doesn't. I don't want to belabor that. Okay. So, a power function. Now, you have a lot of power functions. Most of your basic functions are power functions. Ax squared, that's a power function. X is raised to the power 2. Ax cubed, x is raised to the power 3. Okay? X to the basic reciprocal function, 1 over x. X is raised to the power -1. Reciprocal square function, x is raised to the power -2. And it turns out that the inverse of any power function is a power function. So we're kind of expanding our vocabulary of functions, but we can still understand them in terms of the basic functions. And for exponential functions, it's a multiple of b to the x. Now your basic exponential function is 2 to the x. There is a standard exponential function that we use in calculus, e to the x. And we'll explain that a little bit. Behaves very similar to 2 to the x, but the calculator gives you the values of e to the x. And the inverse function, which is a log, in this case, the inverse function is the natural log of x. The calculator is set up to give you values for those functions, and those functions have very nice properties when you do calculus with them. Okay, so anyhow, just a little overview of why some of these functions are important. And you won't fully appreciate that until you've had a calculus course, and you appreciate it even more if you go beyond that. Not that everybody wants to do that. Okay, so anyhow, a power function fit. Now, a power function is basically x to some power. X to the 3.7 is a power function, just like x to the second, x to the third, x to the -1, x to the -2. X raised to the cube root of 17 is a perfectly good power function. P would be the cube root of 17. Once you know P, you know what the power function is. Now in general, you have some multiple of an x to the P, and that's your more basic power function. Not in the sense of our basic functions, most basic functions, but that sort of thing. Now, we'll say more about that. The point is, there are a lot of cases where you want to have 2 points, and you want to see what power function has a graph that goes through those points. So let's just say that these points are, I'm not even going to bother to scale, let's say that's 8, 5, and if that's 8, then that's probably about, it's more than 2, it's more than a third of 8, so I'm going to say that's maybe 3, and this is maybe 12. Okay, so I've got these 2 points. I want to fit this form. I want to see how to do that. And then in a very similar manner, I've got 2 points over here that I want to fit to the form of an exponential function. Now again, the difference is you got a parameter a in both of them. Your second parameter in this one is p, and it's an exponent. And your second parameter here is b, and that's the base of an exponential expression. Now you'd think, since p is the exponent, you want to tend to confuse power functions with exponential functions. In power functions, x is raised to a power. In exponential functions, x is the exponent. So you focus on what x is, okay? Or you focus on what the exponent is. Here the exponent is your power of x, so it's a power function. It's a power function, yeah. Here, x is an exponent, this is an exponential function. And they have completely different behaviors. So you don't want to confuse those. People always say something grows exponentially when it grows like a power function. It's a terrible confusion because it's very misleading. if you're really trying to think about certain things. Okay, over here, let's say this point is 12, 7, and if that's 12, then this is probably about, might be 5, probably not, but we'll call it 5. And if that's 7, this is, say, 2. Not all that accurate, but it doesn't matter, we're just using this for illustration. Okay, now if I want to fit a power function to these points, you know, you notice that I have 2 points, and I have 2 parameters, A and P. So I plug the coordinates of the points in. Plugged into the form of the power function, I get y, which is 12, equals A times x is 3. That's not very good. A times 3 to the p. And from the second point, I get 5 equals A times 8 to the p. Now I have choices about how to approach this. Okay, I can solve this equation for A. I'm going to get 12 divided by 3 to the p. And I can plug that in for A now, 12 over 3 to the p times 8 to the p. It's going to be 12 times 8 to the p over 3 to the p. Okay? And that's going to work just fine. Okay, so you can do that. It's a little slicker if you simply divide one equation by the other, because if you do, the a's divide out. Okay? So I'm going to divide equation 1 by equation 2. And what I get on the left is 12 divided by 5. Now the right hand sides are equal to the left hand side, so this 12 over 5 has got to equal A times 3 to the p divided by A times 8 to the p. So that a's divide out, I get 3 to the p over 8 to the p equals 12/5. Now, here's why I see a lot of weakness in algebra, and that's why one of the prerequisites for this course is supposed to be pretty strong algebra, pretty good performance in math courses, up through at least algebra 2 and hopefully beyond. So, what do you do with 3 to the p over 8 to the p? Well, it's pretty simple. That's just 3 over 8 to the p equals 12/5. Okay? Now you're stuck. Because unless you understand logarithms, you can't solve for p. We're sort of stuck. We need logs. Now I can show you how to solve with logs very easily, but I'm not going to do it right now. So right now, you know that this is how you fit a power function. You know you get it down to this form. You're going to have to solve for p. And once you solve for p and know what p is, you plug in for p here. You're probably going to get some kind of fraction, rational number, or irrational number. You're going to get 3 raised to that power, though, and you can do that with your calculator, at least to a good approximation. And then you're just going to have a number here you're going to be able to solve for a. So you're kind of stuck, though, on solving for the exponent. You can think about it. You're not going to be able to do it unless you understand logs, and many of you might. Okay, exponential function, maybe everybody understands. That would be great. Exponential function fit, y equals a times b to the x. Well, okay, so we plug in here. Now, this one turns out to be easier to solve. It's actually quite easy to solve just using your basic algebra. Just looking for a good place to do it. I'll do it over here. Sometimes it gets a little hard to see the right-hand side of the board, so I'm moving the board over just a little bit. Okay, so I do the same thing. First point, I didn't label the second point, but okay, we take the coordinates of the first point, plug in to the form. We take the coordinates of the second point, plug into the form. Okay, the first point gives us, careful now, 2 equals a times b to the 5th. Okay? Now, y is 2 and x is 5. So if you put 2 here and 5 here, this is what you get. Okay, the second point is easy enough. Y is 7, so you're going to get 7 equals a times b to the 12th. Then what are you going to do? Again, you can choose to solve this for a and plug the expression in here, and you're going to get a solution. A little more direct, I'm just going to divide the equations. So, now here I divided the first by the second. Here I'm going to divide the second by the first because I just want the number on, the number I get to be 7/2 rather than 2/7. And that's just a personal preference, and I'm not even sure it's a preference, but I'm going to do it anyway. So I get 7/2 equals a times b to the 5th over a times b to the 12th. Very simple. Switching sides and noting that a divides out, I end up with b to the 5th over b to the 12th equals 7/2. Now how are we going to solve that for b? Well, what's b to the 5th divided by b to the 12th? Okay, b to the 5th divided by b to the 12th is b to the -7th. So now I know that b to the -7th is 7/2. And again, people tend to be a little shaky in this next step, but it's very simple. I just raise both sides to the -1/7 power. Now this requires that you really understand the laws of exponents. But b to the -7th to the -1/7, you're multiplying exponents. 7 times -7 times -1/7 is 1. So b to the -7th raised to the -1/7 by the laws of exponents must be just b to the 1. Now I'll write the exponent explicitly. And then you can take your calculator and do 7/2 to the -1/7. Now why did I have to end up with a power like -1/7? That wasn't very good planning on my part. Trying to figure out what number you'd raise to the 7th power to get 3.5. And I can kind of interpolate and stuff. If you raise 1.4 to the 2nd power, you get 1.96, and it gives you about 4 if you raise it to the 4th power. And then if you double that, 6th power is going to be about that. I'm going to say it's maybe 1.3. I think it'll be somewhere less than 1.4. Then 1.3 is a pretty good candidate, and with whatever intuition I got today, that might be an okay estimate. Now you take your calculator and figure it out. That's easy. So you take this then, and you plug it in to either of these equations. Okay, so we plug it into this equation. Now I've got no place to bring this equation, so I'm going to have to take a different color and just cut right through everything. And I can then say that 2 equals a times 1.3 to the 5th, assuming that I made a decent approximation there. Now 1.3 squared is 1.69, so the 4th power would be pretty close to 2.89. The 5th power would be 30% bigger than that, so it would be about 3.7. Yeah, Don't take this too seriously. My estimates are. So A is going to be 2 over 3.7, which is going to be approximately 0.55, something like that. Okay? And you can take a calculator and correct my the errors in my intuition. I don't think I'm too far off with these things, but I could have done something haywire earlier. The process is what's important. You plug the coordinates in to the form of the function, and it's always this for an exponential. It's always this for a power function, if you can see it. I don't know if you can see that far to the left of the board. Yeah, you can probably about see that. And you solve the equations, and in both cases, you're just going to divide one equation by the other, unless you really want to solve one for A and plug that in for A in the second one. That's okay too. It gets you the same point almost as quickly, so I've got no objection. And now you got a model. Okay, so in this case, your model is y equals a times b to the x. A is 0.55 times 1.3 to the x. Just like a multiple of 2 to the x, except it's 1.3 to the x. And you got a multiple out here that corresponds to maybe vertically stretching the graph or relabeling a basic 1.3 power function. It's not really 1.3, I don't know. You can work it out. Okay, so that's kind of it. So we've kind of been over how you model a linear function, a quadratic function, a power function, and an exponential function, except we're sort of stuck at one point here on the power function. And you got to have a couple of rules for operating in logs, and maybe in terms of the log base 2 graph inverse to the 2 to the x graph. You can understand those laws a little bit.